and enthalpy. Understand? There are two things. One is an internal energy. One is an internal energy, and one is an enthalpy. Okay. Now there are different types of enthalpies that we have. First is the bond energy data. The bond energy, and using bond energy, we are going to calculate the enthalpy. Second is the enthalpy of combustion. Enthalpy of combustion. Third would be the enthalpy of formation. Then we have the enthalpy of vaporization. The enthalpy of vaporization. And all of these enthalpies, once you understand, there will be a constant concept of Hess's law. Of Hess's law. So all of these laws will actually include, you know, the law. So Hess's law would be inculcating or would be utilizing all the enthalpies in one. There would be enthalpy of fusion. There would be enthalpy of fusion. There would be enthalpy of atomization. Enthalpy of atomization. Yes or no? So these are the enthalpies that we have. So we have bond energy data. We have enthalpy of combustion. We have enthalpy of formation. We have enthalpy of vaporization, enthalpy of fusion, enthalpy of atomization, and there are multiple enthalpies. It could be enthalpies of sublimation also. So, whatever changes you can see nearby, all of them have certain energy associated with them. And that energy associated with those particular changes, you call them as enthalpy. Do you understand my point? Now, understand when we are doing enthalpy and internal energy. Just see. So, for example, when I am carrying out a certain reaction, okay, obviously the reaction has to be carried out in a beaker only. So, when I carry out a particular reaction, A plus B gives me C or 2C, whatever the reaction is. And I have made sure that, the beaker would be closed. I have made sure that the beaker would be closed. You understand? The beaker would not be open. So this condition that we are making is going to be this is going to be the condition for internal energy. Now, what do you mean by internal energy? That when a particular reaction is being carried out. So obviously some amount of heat would be released and some amount of heat would be absorbed along with that. So it A plus B should give me 2C. I hope you're understanding that some amount of heat will be released during this reaction. Why am I saying that heat would be released? Because I am given a combination reaction. So A plus B would actually be doing what? This is actually a combination reaction. And combination reactions are exothermic. But I hope you're understanding that this exothermic reaction, you know, this exothermic reaction, which is being, carried out in this particular beaker, the heat is being released in a closed container. The heat is being released in a closed container. I hope you're understanding. And when the heat is being released in this closed container, what does that mean? Just tell me. What does that mean? It means that that no more amount of heat would be allowed to escape this beaker, one thing. And second thing, the volume is kept constant. The volume is not allowed to change. So whenever the heat is released at constant volume, because obviously, when the heat is released, the gases might want to expand. But we are not allowing the expansion of the beaker. So we are allowing the heat to be produced, but that heat is being produced in a situation where the volume is kept constant. Are you understanding? The beaker is not allowed to move up and down. The piston is not allowed to move up and down. So then I say that, when the volume is kept constant, at that time, whatever amount of heat is being produced, whatever amount of heat is being produced, you understand? That is called as the internal energy. That is called as the internal energy. But 90% reactions when we perform, when 90% reactions when we perform, either we don't put these nails or we do not even close the beaker, because most of the reactions which do not involve a gas, we can carry those reactions in the open beaker itself. You know that. And when we perform those reactions in the open beaker, what do we have in here? So the reaction is being carried out like this: A plus B shall give me 2C. Yes or no? So what exactly is going to happen? Just tell me. When we have A plus B gives me 2C, what do you think would happen? Just tell me. That amount of heat that we have, that amount of heat that is being released under the atmospheric pressure. So there is no pressure. So, the gases, the heat would be evolved out, and the gases, if they want to expand, they will expand. And even if they are not gases, so no need of the whatever the piston wants to move. Even if I'm closing it with a piston, wherever the piston wants to move, wherever the piston wants to move, I hope you're understanding. Wherever the piston wants to move, it is free to move. If that is the condition, and under those conditions, if heat is being released, so I will say what? That, when the volume is not constant, it is constant pressure. It is constant external pressure. And when it is constant external pressure, that means no matter what is being done inside the beaker, the external atmospheric pressure shall remain constant. Are you understanding? The external atmospheric pressure shall remain constant, and under those conditions, the reaction is taking place. And they are continuously pushing it downwards, and the reaction is happening against this atmospheric pressure. Are you understanding my point? Right? So, this is the concept. This is the concept. So, when we are talking about the constant external pressure, you understand the heat released at constant external pressure, the heat released at constant external pressure shall be called as my enthalpy. So there's a difference between enthalpy and there's a difference between internal energy. Do you understand my point? Right. Internal energy is associated with the constant volume, and enthalpy is related with the constant pressure. You understand? Now, just see. What do we have in here? Just see. We have this particular part, right? We have this particular part. Now, when I say enthalpy of formation, now that's an important part. Enthalpy of formation, how do you define enthalpy of formation? Write it down. Enthalpy of formation is the heat absorbed or released. Is the heat. Generally, when something is being formed, obviously it has to be stable to be formed. So, and when something stable is being formed, heat is generally released out. So, I will say that the heat of formation means the heat of the formation of 1 mole of a substance, of 1 mole of a substance. Heat of formation is basically the heat of 1 mole of a substance, heat of the formation of 1 mole of substance from its most abundant, from its most abundant reactants, from its most abundant reactants. You understand? That is enthalpy of formation. And most abundant and stable reactants. You understand? So, heat of formation of 1 mole of a substance from its most abundant reactant. That would be the enthalpy of formation. So, how would that be? Just understand. So, I would say most abundant and stable reactants. So, for example, you understand when we talk about oxygen, right? When we talk about hydrogen, when we talk about carbon, when we talk about sulfur. Now, these are the elements which exist in nature. We do not know how they came about. You understand? Oxygen, you can have a fair idea that okay, oxygen in the atmosphere is due to the plants. But my point is that when there were no plants, when the earth just started to develop, then what do you think would happen? Tell me. Then what do you think would happen? O2. O2 Existence, I do not know. I know that, O2 exists in nature and O2 is a lot in abundance. That's all I know. When I'm talking about carbon, I do not know how carbon under the earth came about. One we know that, the molecules of the land and the dead animals and plants, they get decayed and decayed, and soil got deposited over them, and then everything converted into carbon. That is one definition, one method. But obviously, there might be different methods in nature which would be able to produce this particular, carbon. So the exact method of production is not known to me for carbon. Same for sulfur also. I hope you're understanding. And also, what I'm trying to explain you, that carbon, if it exists in nature, it exists either in the graphite form primarily, or it exists in the diamond form. You understand? But out of graphite and diamond, carbon is most stable in the graphite form, and carbon is also most stable in the is most abundant in the graphite form. So you might say that, abundancy of carbon is where? You tell me. Abundancy of carbon is where? Diamond is also equally stable. Who said that diamond is not stable? Diamond is way more stable. But diamond is not that abundant. The amount of diamond in nature and the amount of graphite in nature is a lot of difference. Diamond is way too less in comparison to that of graphite. So what my point here is, when we are talking about graphite and when we are talking about diamond, so both of these are the forms of carbon. Both of these are the forms of carbon. But in these forms of carbon, what you get to see, that graphite is more stable and abundant. Similarly, if I talk about sulfur, okay, sulfur, I have rhombic sulfur in nature and I have monoclinic sulfur in nature. But a more stable form of sulfur is rhombic sulfur. A more stable form of sulfur is rhombic sulfur. Are you understand? Right? So this rhombic sulfur that we have, you understand? This rhombic sulfur that we have is going to be more stable and more abundant. So now, when something is actually more stable and more abundant, I will say that, this naturally existed in nature. For me, I will assume that carbon in the form of graphite naturally existed in nature. And I do not know where it came from. And when I do not know where it came from, I will say, that its formation, that I do not know what is its heat of formation. It just existed in nature. So for me, the standard heat of formation for graphite would be zero. Are you understanding my point? The standard heat of formation for graphite would be zero. I hope you're understanding my point. Hmm? Same is the case with sulfur. So if something is more stable, something is existing in excess quantity. So obviously the nature is supporting it, it's supporting the formation of that particular element. And when the nature is supporting the formation of that particular element, I hope you're understanding that, I do not know what natural process is actually supporting it. So for me, it is just existing. So I would conventionally, okay, this is just a convention, that conventionally, I do not know whether the formation is exothermic or endothermic. So I will take that heat of formation to be zero. For all naturally occurring, naturally occurring, for all naturally occurring more stable substances. Do you understand my point? You understand? So now when I say that, carbon dioxide has to be formed. Now, carbon dioxide formation is in my hands. I can do what? I can take some amount of carbon and I can burn it in oxygen and I can see that carbon dioxide shall be formed. Now, obviously, carbon dioxide is definitely, and now see, understand, every reaction will either be exothermic or will either be endothermic, right? Some amount of energy will be released or absorbed. And we know that, this is actually what? This is actually the combustion of carbon. This is actually the combustion of carbon. Are you understanding? So, when this is the combustion of carbon, what does that mean? You tell me. This is the combustion of carbon. What does that mean? So, carbon is in the form of graphite if I burn, then also carbon dioxide is formed. And carbon, if I burn in the form of diamond also, then also carbon dioxide shall be formed. You understand? So when carbon is being combined in the form of diamond, then also carbon dioxide shall be formed. And when carbon is in the form of graphite, then also carbon dioxide shall be formed. First thing first is that amount of carbon dioxide formed is nothing but 1 mole. So that is my definition of formation, enthalpy of formation. Read it out. It says the amount of heat released, the amount of heat released f- for the formation of 1 mole of a substance. The amount of heat released for the formation of 1 mole of a substance. So in the reaction, you have to say that, ma'am, in both of them, so this is delta H reaction and this is also delta H reaction. So let us suppose some heat is being released minus 100 kilojoules per mole. And here also some energy is released, let's suppose minus 80 kilojoules per mole. Yes or no? So here heat release is minus 80 kilojoules per mole and here heat release is minus 100 kilojoules per mole. I hope you're understanding. So when the heat released here is minus 100, but you understand that obviously these two are two different reactions. So when these are two different reactions, I hope you're understanding that amount of heat released is actually what? Tell me. The amount of heat released is actually what? The heat released during the happening of this reaction is the heat. But which heat will I call the heat of reaction, heat of formation of CO2? So I'll say that the heat, the CO2 has to be formed 1 mole. And from where CO2 has to be formed? The CO2 has to be formed from the most stable, abundant element. And the most stable, abundant form or the reactant would be what? Carbon in the form of graphite. Are you understanding? You understand? So I will call that, heat, no matter how much reactant is used. First thing first, that the product should be 1 mole. The product should be 1 mole. And secondly, that graphite is being combining with O2. So when carbon in the form of graphite is being combining with O2, so CO2 shall be formed. Do you understand my point? And when CO2 shall be formed, what does that mean? You tell me. When CO2 shall be formed, what does that mean? You tell me. But that CO2, 1 mole, that is whatever is being formed, should not be formed from something which is not stable, should not be formed from which is not very abundant. So I will say that, the reactant, no matter what reactant you're utilizing, but the amount of product that you have to form shall be 1 mole from its most stable and abundant element, reactant. Most stable and abundant reactant. And if this is happening, so this heat of reaction shall be called as a heat of formation of CO2. Because every reaction will definitely have some heat involved in it, right? Some amount of heat lost or gained. So heat of formation of CO2 will be the heat of reaction for that particular reaction where 1 mole of CO2 is formed and from its immediate reactants. So to form carbon dioxide, carbon is needed and oxygen is needed. So in immediate reactants I would be needing. See, obviously you understand, ma'am, carbon dioxide is also produced when I burn methane and oxygen, definitely. Then also carbon dioxide is formed. And then also 1 mole of carbon dioxide is formed. But do you find the formation of carbon dioxide from carbon and hydrogen, from carbon and oxygen? No. So the reactants have to be the elements of the compound that is being framed. So, for example, if I have to write down the formation of, let's suppose, water. So H2 plus O2 should give me H2. And let's balance this equation. So if I write down this, I'll put it here like this. So there would be some heat involved here in the reaction. Let's suppose the C is minus 200 kilojoule per mole. And if I write down, it shall become H2 plus half O2 shall be H2O. Now, what is the difference between these two reactions? Here, the delta H reaction shall be minus 100 kilojoules per mole. Yes or no? What is happening here? You tell me. What is happening here? When we have 2H2 plus O2, I see both the reactions are correct, no doubt about it. H2O is being formed from H2 and O2, that is the requirement. But how much amount of H2 should be formed? 1 mole. But here 2 moles are being formed. Here, 2 moles are being formed. Are you understanding? And when 2 moles of H2O are being formed, what does that mean? You tell me. When 2 moles of H2O are being formed, what does that mean? You tell me. That, ma'am, that this reaction definitely it is a correct reaction. This reaction definitely has H2O being formed. But according to the definition of heat of formation, 1 mole of H2O should be formed. In that reaction where 1 mole of H2O is being formed, what do you understand we have? Tell me. When 1 mole of H2O is being formed, you tell me what is going to happen. Only then we'll be able to write it down per mole, isn't it? That amount of heat released per mole is this much. Because that is the heat of formation. I hope you're understanding. Right? Because how do I define that? If I know that 1 mole substance is being formed in nature and it requires 50 joules of energy, so then definitely I can create an estimate that if 5 moles is to be prepared, then 50 into 5. So heat of formation has to be defined for 1 mole substance. And how do I define heat of formation for 1 mole substance? Because if I'm forming if I'm forming 1 mole product in that particular reaction, are you understanding? So what do you think we have it right here? Tell me. What do you think we have it right here? So this reaction is heat of reaction. This reaction also has a heat of reaction. But I will call this heat of reaction as the heat of formation. Because in this, the H2O is being formed from its elements, and H2O is being formed in 1 mole quantity. And H2 is being the most stable isotope, which is the protium, H11, and the most abundant also. And O2 is that is being used is also the most stable and most abundant. Do you understand my point? Yes or no? Right? So now when we have the equation like this, if I say sulfur dioxide, so if I write down S8 plus O2 gives me this. And here I'm saying sulfur is being used in the form of rhombic sulfur. And here I'm burning monoclinic sulfur plus O2 to give me SO2. So let's first balance this equation. So I'm going to write down 1 by 8 here because my condition is to prepare 1 mole of SO2. So 1 by 8 here. Reactants, I can do any amount of reactant, but the product should be 1. So this reaction will have some amount of heat, let's say minus 500. And this reaction will also have some amount of heat being released, which would be minus 700 kilojoules. You understand? But what is happening? Which reaction's heat will you call it as a heat of formation? The first one. Why? Because the rhombic sulfur is the most stable. The rhombic sulfur is the most stable and the most abundant form of sulfur. You understand? So you will have delta H reaction will be minus 500 kilojoules. Understood or not? Right? So this shall be the heat of formation. Any doubts in this? Okay? That is the concept. That is the concept. Understood? Right. Hmm? Okay. So this is one thing. Next, we have the heat of combustion, the enthalpy of combustion. The enthalpy of combustion. Now, enthalpy of combustion is actually defined for all the compounds. What is enthalpy of combustion? It is the amount of heat released, amount of heat released during the combustion of 1 mole of a substance. During the combustion of 1 mole of a substance in the excess amount of oxygen. In the excess amount of oxygen. So amount of heat released during the combustion of excess amount of oxygen. That is called as the enthalpy of combustion, right? So for example, if I write down the equation, it's very simple. There can be a lot of combustion reactions. Like for example, if I say sulfur S8, or if I write down um, COCH4 plus, or let me write it down like this, C3H8, right? Plus, or if I write C3H8 plus H2 plus O2, and if I balance this equation to give me CO2 and H2O. So who am I combusting here? I'm combusting propane. I am combusting propane, isn't it? When I am combusting propane, I hope you're understanding. I'm combusting it and I'm getting CO2. Let's balance this equation. So I get 3 here. And to hydrogen, I will have to put 4 here, because there are 4 times 2 is 8. How many oxygens do you think we have? We have 3 times 2, 6. 6 and 4, 10. So I'm going to put 5, 10, and 5 right here. So that's my balanced equation. So some amount of heat would have been released in this, right? So some heat released, RXN. RXN means heat of reaction. So in this heat of reaction released would be what? Let's suppose some 500 kilojoules of heat is released. Heat released, I'm going to put it as minus per mole. So when the heat released for the reaction is minus 500 kilojoules per mole, I hope you're understanding that delta H reaction equals to minus 500 kilojoules per mole. And definitely per mole is, I'm writing that's correct. Why? Because you understand that, here 1 mole of propane is getting combusted. This equation is actually showing me I do not care about how much oxygen is being used. Oxygen can be in excess. I do not care about how much CO2 is being produced. I do not care about how much water is being produced. Do you understand? But the amount of propane that would be produced is going to be 1 mole. You understand? The amount of propane that I'm combusting is 1 mole. And this equation, this heat is being showing the amount of heat produced when 1 mole of propane would be combusted. Yes or no? So, for example, if I give you C5, if I give you C5H12, so 6, yeah. So, if I give you C5H12 to combust, C5H12 to combust fully, so I will get CO2 and water. Obviously, after combustion, CO2 and water is being formed. So that would mean if I balance out this equation, I'll have to put 5 CO2 right here and I will have to put 6 here. Yes or no? Right. Let's make it C5H10. C5H10. Why C5H10? Because I'm trying to combust an alkene, which is pentene. And if I'm combusting pentene with O2, I will get 5 CO2 and H2O. If I get 5 CO2 and H2O, so to balance out carbon, I have 5 carbons here, I'm going to put 5 here. I have 10 hydrogens, I'm going to put 5 right here. So what do you think we have in this equation? We have 5 times 2 oxygen, and 5 times 1 oxygen will 15. So how do I balance it? I will put 15 over 2 right here. You understand? The equation that the people will give you would be this. It would be what? It would be 10 here and it would be 10 here. You understand? Exactly. So the equation would be given to you like this, and they would give you delta H reaction would be minus 1000 kilojoule per mole. Let's suppose this. So obviously, if they're giving out this particular reaction, heat is being released. But I hope you're understanding that C5H10, 2 times C5H10 is pentene. And when we have 2 times C5H10 is pentene along with O2, this reaction is actually showing the combustion of 2 moles of pentene. And when this reaction is showing you the combustion of 2 moles of pentene, what do you understand would happen? Just tell me. When this reaction is showing you the combustion of 2 moles of pentene, you understand. So what do you think would happen? Just tell me. That we have, we cannot call this reaction as the heat of the reaction to be the heat of combustion. Definitely there is some heat, obviously, you will call it as heat. No other name for that. But you can't call this heat as the heat of combustion. That's the logic. I hope you're understanding. Right? So that is the concept. That is the concept. Okay? Right? So that's how we sort of work with this heat of reaction. So I will have to do what? I will have to divide this equation with what? I will have to divide this equation with 2 everywhere. And if I'm dividing this equation with 2, I will also have to divide the energy with 2. I will also have to divide this energy with 2. You understand? So what do you think I will have? I will have 2 times C5H10. So I will have to divide this. It is going to become C5H10 plus 15 over 2O2 to give me CO2 plus H2O. Yes or no? So I will have what? This is going to become 5, this is going to become 5, this is going to become 15 over 2. So for me, it is going to become 15 over 2 and 5 and 5. And the heat also I will have to then divide, and it is going to become minus 500. You understand? So that is how this question is going to be. So first thing that you have understood is that, every reaction has some heat involved in it. But which reaction's heat would be called as the heat of formation? You have to see according to the definition. That 1 mole substance should be formed. 1 mole substance should be combusted. And secondly, it should be a full complete combustion. If I say that, CH4 is being combusted and carbon monoxide is being produced and water. So carbon monoxide is being produced when it is incomplete combustion. When it is incomplete combustion, yes or no? And O2, this is limited. I hope you're understanding. And if I have CH4, if I write down O2 in excess, only then the combustion shall be included into the category of, so that the heat involved in this reaction, I will be calling it as what? I will be calling it as what? Heat of reaction in this case would be called as the heat of combustion. Delta H combustion. So according to the given definition, you have to give specific names of heat of combustion, heat of formation to a particular reaction. And what am I trying to explain you right here? That if I have this equation, let's suppose I have A plus 2B gives me 3C plus 5E. And I have some heat given with it. Let's suppose the heat is 100 plus 100 or minus 100, whatever it is. So one thing you have to understand, negative sign indicates that the reaction is exothermic. That lot of heat is actually being produced here. So one, if you reverse the reaction and you write it down again, right? So forward reaction is shown to be exothermic. And if you reverse a particular reaction, you see that it is going to become 3C plus 5E shall be written down like this, A plus 2B. Then the heat shall also become reversed in sign. So it is now going to become 100 joules. You understand? And this minus 100 represents exothermic. So plus shall represent endothermic. Plus shall represent endothermic. You understand? If, for example, this is my main equation, and if I write down this particular main equation as what? If I write down this main equation as what? If I write down this main equation as, if I multiply this equation with, let's suppose, 2. So 2 times A plus 4B gives me 6C plus 10E. So then the heat also I will have to multiply with 2. So that shall become then minus 200. I have not changed the order. A and B are remaining in A and B, and C and E are remaining in C and E. I hope you're understanding. So when the order is not being changed, So the value still remains exothermic, but the amount of heat released would be definitely more because you are now utilizing more reactants. So more reactants will produce more products, will produce more energy. More reactants will produce more energy, isn't it? I hope you're understanding. And if I reverse it and then I add it up, so that's how the case is. So first thing is that when you reverse the equation, the exo will appear to be endo, and that change you will see in the sign. Minus will become plus, plus will become minus. If you want to multiply a particular equation with a particular number, let's suppose I have multiplied the entire equation with 2. So 2 times 8, 2 times 2 4, 2 times 3 6, and 2 times 5 10. So if I'm multiplying this entire equation with 2, what does that mean? You tell me. So the equation shall become 2 times the value of 100, and that shall become minus 200. I hope you're understanding. Okay, so that is the concept. So that is the concept.